Okay, so following the lecture parts of the pathology image analysis, then we move on to the workshop, and it's a very exciting part of the course because I know some of you may be nervous about the case presentation too, then how to write some codes to do the differentiate the skin images, to differentiate the nevus and the melanoma. So in this workshop, I believe that I can show you the actual the practice of the CNN training, so you can apply the knowledge from this workshop to the case presentation too. Okay, so I found a public data sets on the Kaggle websites. That is, it is the breast histopathology images containing a large collection of the intra-invasive ductal carcinomas and also non-tumor parts of the cell scanning. So I already provide you the link to this database, and you can look at this database to see the descriptions. So I'll just read this for you. So invasive ductal carcinoma is the most common subtype of all breast cancers. So to assign an aggressiveness grade to a whole mount sample, pathologists typically focus on the regions which contains the invasive ductal carcinoma. As a result, one of the common pre-processing steps for automatic aggressiveness grading is to delineate the exact regions of IDC inside of the whole mount slice. So it means that for the pathologists need to develop an algorithm to help you identify how many regions in this sample is the cancer, but not the benign tissues. So the large amount of the cancer tissues will just have a higher grade of the aggressiveness of the invasive ductal carcinoma. So that is one practical example we need to solve. And if you are interested, you can download this whole data sets, and the whole data is about 1 gigabyte, but already provides you a smaller amounts of the data. But before that, let's take a look at what are the types of the breast cancer. So the breast cancer is a very common tumor for the women. And there are several types of the breast cancer, but the most common two types are the ductal breast cancer and lobular breast cancer. And there are also other breast cancer, which is the mucinous and inflammatory or mixed tumor breast cancer. But the most common types are the ductal and lobular. Because in the breast tissue, there are the duct tissue to you let the breast milk to secrete from these breast glands, and from using this duct to outside the breast to the infant to suck into the infant's mouth. And so the lobular tissue and the duct tissues are two sites that can have the cancer cells. And for example, if you have the cancer cells just within the size of the tissue, then we call this the carcinoma in situ. It means that the cancer does not invade it into the outside the range of these parts of the tissue. So for example, these show you the normal duct cells. It's just like a duct. It's a tunnel. But if it has a cancer, then it will just grow into this duct. You can see that it should have one layer, but in this case, it has more than one layers of the ductal carcinoma. And for the lobular carcinoma, then is a normal lobe cells, then in the lobular carcinoma, it just grows into these lobes, so just congested these tissues. So in summary, that is the carcinoma in situ is the growth of cancerous cells inside ducts or breast, and in the case of the lobular carcinoma, it's overgrowth of a non-cancerous cells in lobes or breast. But the most important part is that the abnormal cells haven't spread to the other parts of the tissue. So we call this a stage 0. Okay, so there's a very small cells inside the glands, and there's no invasion into the lymph nodes, and it just confined to the breast area, not outside. And usually, if you can identify the cancer in this stage, the 5-year survival rate is almost 100%. Means that if you just remove the pathology, then remove the cancer, you will just cure this cancer. And in the stage 1, the tumor is a little bit larger, but still less than 2 centimeters. And there's still no invasion into the lymph nodes. So in that case, the survival rate is still very high. And in the stage 2, the tumor is larger, the size is between 2 and 5 centimeters. And in this stage, usually the cancer has been invaded into the lymph nodes. So, but it's still confined to the breast area, not outside of the breast. So just like showing in this region, the cancer just spread into the near adjacent lymph nodes, but not the other parts of the body. So in that case, because the cancer cell already migrated to the lymph node, it has a high chance to develop further into the other parts of the body. So the survival rate will be reduced further, just like in the 87%. In the stage 3, because the tumor is larger, the survival rate is even lower. And in the stage 4, the cancer has spread into the other parts of the body. So in that terminal stage, then the survival rate will be very low. So that's why it is very important to identify the cancer in an early stage, then so you can have very high chance to cure the cancer. And we often use the so-called TNM system for the staging breast cancer. The T means for the tumor size, and the N stands for the lymph node status, and the M stands for the metastasis. So the tumor size just means that we can measure the tumor size and divide into the 0 to 2, 2 to 5, and larger than 5, or broken through skin or attached to the chest wall. And for the lymph nodes, just a kind of a subjective finding from the physical examinations. If you can feel the lymph nodes will be the N1, and if it is swollen and lumpy, then it will be N2, and if it's located near the collarbone, then you will stage into the N3. And for the metastasis, it's very simple. If it's metastasis to the other parts of the body, then yes, the metastasis, and then otherwise you just the non-metastasis. Okay. And so to determine the stage of the breast cancer, we need to do the biopsy, which means that you need to extract a small amount of the tissue from the abnormal tumor in the breast. So in this figure, you can see that this is the demographic, demonstrative figure from a Mayo Clinic. Then you can just use the ultrasound and use the needle biopsy tool and use ultrasound to guide the needle to pierce into the mass in the breast. and to extract a small amount of tissue and to do the histopathology scanning. So that is how we obtain the data sets we used in this course. And it is based on the core needle biopsy. Okay, but to ensure that the needle will just get into the right place, you need to ultrasound. So it is very technical driven. That you need to have a very, you need to train highly trained technicians or doctors to do this kind of job. So for this data set, the rationale is that because the breast cancer is the most common form of cancer in women, then also the invasive ductal carcinoma or IDC is the most common form of the breast cancer. So accurately identifying and categorizing breast cancer subtypes is an important clinical task, and automated methods can be used to save time and reduce error. And I just copy and paste the description of this data set so you can have more insights into this data. So I just read this for you. The original data sets consisted of 162 whole mount-slice images of breast cancer specimens scanned at the 40x, means that using the 40 times of magnification of the original slides. And from that, about the 277,000 patches of size 50 by 50 pixels were extracted for these data sets. So this contains the 198,000 IDC negative patches and 78,000 IDC positive patches. So this means that from the high resolution pathology images, you just divided this into 50 by 50 pixel squares and use these squares and you just label them as the IDC positive, means that in that small regions, it contains the cancer cells. And also for the other parts of the patches, you will just label for negative. But negative doesn't mean that this is the normal healthy controls, but just means that these parts of the tissue do not have cancer cells. So this is just try to clarify that this data is not from, it's solely from the patients, but there are no healthy controls in this data. But the healthy control is that the tissues without the cancer cells. You can also say that it is healthy or normal tissues. Okay, so each page's file name is of the format like this one, so you can easily identify the results of this file. For example, the U means the patient ID, and the X means the coordinate of where this patch was cropped from, and Y is the Y coordinate of where this patch was cropped from. So it can look at the X and Y to reconstruct the original whole mount-slide images. But in that case, we just focus on this class. The class C try to label this as the 0 as the non-IDC and the 1 as the IDC. Okay. So this is the for the convenience, for your convenience, I just extract 1,000 versus 1,000 patches from the original data set, so you can process this data without any burden put on your computers. So this is one of the examples. If you just look into the unzip files, and you can see there's normal parts of the tissues. Okay, so it's a very small patch. It's only 50 by 50 size in the images, and this is the parts of the invasive ductal carcinomas. So you can see that even for this one, you can see a majority parts of the normal parts is just there's no tissues, or there's normal parts of the tissue that do not have the cancer cells. But in the case of invasive ductal carcinoma, then you can see that there are just the cancer cells that can identify in these small parts. So for this 1,000 versus 1,000 data sets, it's still very difficult using the conventional method, for example, the logistic regressions, to do the machine learning, because for the logistic regressions, you need to derive some image features from this data, but it's not easy to just derive the useful features. Okay, so if you download these small data sets from the email or our laboratory websites, then you should be able to find that there's a directory called the breast histopathologies and also some MATLAB codes. So these codes I will provide to you to you do the CNN training. And if you just open into this breast histopathology folder, you will see there are two subfolders, which is 0 and 1. And I also attach a label.txt files to show you the label of these folders. So for 0, it means that it's a non-tumor parts of the tissue images. And for the label 1, it means the invasive ductal carcinoma. Okay, so let's just show you how to read image data. So remember in our first workshop, I showed you how to read the chest X-ray images using MATLAB. So at that time, because the chest X-ray was stored in the DICOM format, so I used the DICOM read to import that DICOM images. But for these pathology images, it's just conventional image format, so it's called the PNG. So we just use the IMRead as the MATLAB functions to read these images. So I just show you, you can just type into the 0 folders, and you can find these files, and you can type in the MATLAB, it's the ing equals to IMRead, or in the input the file name, then you use the IMShow, you can show these images. Okay, so the result will be shown just like this one. And you can see that because it's a 50 by 50 pixels, you can see that the resolution is actually it's not very good, but just a very, very small parts of the tissue from the whole slide imaging scan. And here I just follow the standard CN example I showed you in the previous week, and to show you the 20 random images. So in this case, I'll just explain to you each line of the code. So the first thing, you can try to identify the all PNG files in your one of the subdirectory. For example, if you open into the 0 folders, then you can type the files equals to the dir, which is abbreviation for the directory. Then you can scan all the PNG files, use these the strings, which contains the extension of the files, the .png. Then there's also an asterisk to show you can just want to find all PNG files regardless the file name. So for this line of code, it should give you the 1,000 file name results of the variables. Then you try to create the new figures. Then you use the rand perm to identify the random 20 integers from the 1 to 1,000. So for this perm, we just try to identify the 20 random integers within the 1000 because the total file numbers is 1000. So we just only want to find the 20 of them. So for this 20 index, then we use the subplot to read and plot these images. So this is very similar to the previous slides, but I just replace the file names with the index using the perm. Then I just show these images in the subplot of the whole figures. So the result could be this one. And so you can see these all patches are from the different parts of the whole slide scanning, and it's actually very difficult to extract certain features just based on this small part of the data. And so remember in the previous course, I showed you how to use the standard MATLAB examples to do the digit classifications. However, if you remember in that course, there is the first step you need to load image data store variables, which is the default database in the MATLAB. But in this data, we need to create an image data store to allow the MATLAB to process and to further be trained by the CNN models. So here I just provide you an image to data store functions that is written by me, and it's very easy to read all images and to create image to data store variables. So for any functions in the MATLAB, it just to define the input and output. So in this case, the input is the data path, which is the path of the data images. In our case, is the root folder of the breast histopathologies. And you need to also specify the file extension. And so the codes will need to know which kind of file you need to create for the image data store. So for these codes, the first part, you just get the folder list. So remember in the previous, like in the breast histopathology, we have two folders. One is 0 and the other is 1. So it means that we have two labels. So I also want to emphasize that this is one example of AI-ready data sets. So there's no the universal definition of the AI-ready data sets, but so-called AI-ready data set, it just try to structuralize everything you need to train for the neural network or machine learning models. So we need really a structural data to do the machine learning. So we don't want a folder just contain everything, but we don't know which one is the which label. So in this case, the AI-ready data sets is that you need to put everything under a specific label, so you can use the computer codes to read this label. So for these codes, we need to get folder list, and each folder is actually a label. So we create image data store using the folder name and input file extensions. So you can study this code further, but just for now, you can just specify the data path and the file extension, and this function will do the job for you. So you can just type, for example, under this the root folder in the breast histopathology, you can type the IMDS equals to image to data store, and the input is the present working directories, which is PWD, and also the extension is the .png. Then you will create an image data store, IMDS variables, and which is in the format of the image data store. In these variables, you can see that there are 2,000 files being read by these functions, and you also create labels of 2,000s. You can double click on that one. You can also double click on the files. You can see that it already just store the file path for every image files for you. And also it has a read function. You can specify the read function here, which is the read data store image. Then it's actually the standard function to read images into the computers. Okay, so this is the standard image data store format used by the MATLAB, and we need to use this format to do the machine, particularly the neural network training. Okay, so I will go through each steps of the construction of the neural network, and so just follow these steps and you will derive the final models for these data sets. So the first thing we need to consider is to count the number of images for each label. And because it is very often that you have data with unbalanced label numbers, unbalanced number of the data in each label. For example, if you want to download the original data here, then you should have 78,000 IDC positive images, but you have a larger number, is 198,000 IDC negative images. You can still also use this whole data to train your model, but it is unbalanced data. And it is ideal in the neural network or machine learning training that you should have the balanced number of the files in each label. So for this one, I just want to count the number of the files in each label and to derive the label count. So you will see that if you have an unbalanced number of the data, then I will provide another code here to calculate the minimum label count. So you will avoid the unbalanced separation of the training and testing data sets. Okay, so next step is to try to measure the image size. So we just read one image from our image data store, then we use the size functions to determine the size of the images. And in this case, because our images are colored images, so there will be 50 by 50 by 3 layers. But if there's only 2 dimensions in our images, then we just specify the third dimension to be 1. This is just for the standardization purpose to make sure our parameters will be universal for every case. Okay, so next step is to try to divide the data into the training and the validation sets. So here I just use the 70% as our training ratio, means that we will divide the data into the 70% as the training data and the 30% as the validation data. So the number of trained files will be based on this ratio, and use the minimum label count to derive the number. So I just use another built-in code which is called split each label functions to divide the IMDS, which is original data stores, into the training and testing. So if you execute this code, you should be able to see there are 2 variables generated from this code, which is the IMDS train and IMDS validations. And these are also image data store format if you open, double click on this variable, you can see that there should be 700 cases in this data store variable, and there are 300 files in this image data store variables. Okay, so from now, then we are enter a very important step, that's to prepare our data and to know that the size of our data. And the next thing is that we need to build our convolutional neural network architectures. So for simplifications, I'll just follow the simple example here. Remember that in the convolutional neural network, we need to determine the size of the filters and number of the filters. Remember that in the convolution layers, we use a small parts of the two-dimensional matrix as a filter to match certain patterns from the original data. So these convolution layers will need to define what is the filter size and how many patterns you want to generate from these different filter, different patterns of the 0-1 patterns in these filters. So for the simplification purpose, we just use 3 and 8. Then we follow this parameter to build a series of convolution and the pooling layers in the next step. Okay, so this is the CNN architectures we built. We followed from the digit classification examples. So in this CNN architecture, there are only few layers. These layers include the 3 convolution and max pooling layers. So you can see that the data will go through the first convolution and the batch normalization and the redo layers and the first steps of the max pooling, and go to the second iteration of the convolution, normalization and redo, and the second round of the max pooling, and the third rounds of the convolution, but there's no max pooling at this time, but only try to flatten this data to the fully connected layers, and finally connect to the softmax layer to give a probability of the classifications. So this is the whole thing that we need to specify in the architectures of the convolution neural network. And of course, you can, if you are need to improve the model, you need to design your own CNN model. For example, you can add more convolution layers, or you can try to develop a more complex architectures, just like ResNet or AlexNet. So that is another topics of the workshop, but I will not show you this time, but I will show you in the next course. But for now, you should be able to follow this simple convolutional neural network to do the deep learning classifications. Okay, so another thing is that we need to specify the training options. So you don't have to study every detail in this option, because this is kind of hyperparameters, and the things that for example, you can specify the max epochs, so you can do lots of the training, and if the higher number means that you will do the large number of the training. You will take more time to finish to train your models, and also you can specify if you want to see the training progress here and to see the final results in the real time. So imagine that you already input all those codes, then you can start the CNN training, and it's very simple. Just use the train network functions and specify the layers and options, and you can start the training. I also attached two codes here, which is the ticks and talk. The tick tock, it means that you try to count how much time has passed during this for this codes. So these codes will tell you how long would this training take in your computers. So in my case, I will just, if I execute these codes, it would take about 32 seconds to finish the training. The speed might be different in your computers depending on your the level of the hardwares, but usually it should not take long because I only give you 1,000 versus 1,000 data. So, but it is the results from my computer, so you can see that the overall the validation accuracy is high. And again, you can see that the blue line specifies the training accuracies, but the more important thing is that you need to look at the validation accuracies. If there's a discrepancy between the training and the validation accuracy, it means that the model has overfitting problems. But in this case, you can see that the training and validation accuracy actually are very similar. It means that they are comparable to each other's, and you can trust your final models because there's no overfittings. And also you can see here that the loss of the training models has been declined over time, but the validation models, the loss in the validation still has a very gradual decline compared to the training loss. So you may want to try, if you want to have more training epochs in these parameters, so you might achieve the higher accuracies. So I encourage you to try different parameters to see if you can improve the accuracy. Although in this case, the accuracy is high enough, it's 94.5%, but you may want to change the parameters and to see if you can improve the accuracy further. So I will leave that to you to practice on yourself. And the final thing is that you want to compute the accuracy. So you need to use these trained models to apply this to validation data sets to derive the prediction labels. And you need to compare these prediction labels with the validation label to derive the accuracy data. This value will be the same as you shown on the training progress windows. It should be 94.5 in my case, but it will be the different numbers in your training because each training has a random parameters. So you will probably see the different numbers, but it should be close to this one. And also you can plot the confusion matrix by using the plot confusion functions. So in this case, you can see that we have in the validation data sets, we have the 300 cases, the IDC data divide to be classified as the IDC. The 279 cases over 300 classified as IDC. And the overall accuracy is the green number of the summation of the green box divided by the total number of the cases. So here you can see that the overall accuracy is the 94.5. Then I encourage you to look at the definition of the sensitivity and the specificity to derive the corresponding metrics. So that it would be the fun part. I'll leave that to you also. But most importantly, I already compiled a single function for you. So I just save your time, and you can just specify some parameters, and then you can do everything as I shown you in the previous slides. So these functions has also some input parameters. So first thing, you need to input image data store variables, and you need to specify the ratio of the training to the validation, and usually we put the 0.7 here. And you can also specify if you want to show the training progress. So if you want to just start the training and to take a nap or even go to sleep, that's fine. Then you can just leave the progress here as a 1. Or if you don't want to see the progress, you can specify the number as a 0 here. And you can also specify the filter size and number of filters. And if you want to change the layers, you can just try to modify this code. Just welcome to do anything modification for your own purpose. Okay, so the outputs will be the 3 things, which is the net info, and the net stats. Then we will also require another code I provide in this course. So you can use this a simple CNN code to do the complex job. So the purpose I wrote this CNN code is that you can run CNN at a very few lines of code. In this case, you just need 2 lines. The first thing, you need to use the image data store to create the image data store variables. And the next thing is you need to use CNN functions to create your results. Okay, so I believe this is most simple CNN course in the world, because you just need these 2 lines to do the deep learning. But I will just mention some challenges, and I will leave this challenge to you to think about how to do this kind of job. For example, if you want to develop an AI pathology system, then you need to label the cancer cells on this host line imaging. Then because the data I provide you is crop images from the host line images, so you need to consider if you can show this kind of heat map from your results. Okay, so that is one of the interesting challenges for you to develop practical pathology AI applications. And another challenge is that there are other types of the breast cancer. For example, the lobular type of the breast cancer, and the morphology is different. So if you need to develop a practical AI algorithms, then you need to have an algorithm that can do the multi-label classifications. And for this purpose, you need to find the lobular data to do this kind of job. And unfortunately, I do not have the data for the lobular breast cancer, but if you are working in the medical fields, then you should be able to find the collaborators to do this kind of research. But just want to emphasize that we always need a multi-label classification, just like we want to find out if the image contains the trees, the dogs, and the cats, animals, and or any persons. So that is always we have the multi-label challenges in our imaging deep learning. So I hope you that you can practice on these data sets and learn how to do the case presentation too. And you are also welcome to modify the codes I provide to you, and also try to study the codes to learn how to do the deep learning in the medical images. Okay, so enjoy the course, and I hope you can do the case presentation too without any hurdle. Okay, thank you very much.